Welcome back to The Explainer, everyone. Today, we're diving into something absolutely high stakes and honestly pretty mind-blowing: surviving the literal extremes of the cosmos. We're pulling our insights straight from Dr. A. Abuftooth's course on spacecraft systems design. We're going to look at exactly what it takes to build a machine capable of surviving the most unforgiving environment known to humanity. It's an energetic, high-pressure topic, so let's just jump right in.
Okay, first things first, let's establish what we're actually dealing with here. According to the source material, a spacecraft is, at its absolute core, just a structure that holds all subsystems together. Think of it like the vital skeleton of the entire mission. Without this foundational architecture, your propulsion, life support, navigation, well, they're really just loose parts floating around in a vacuum. This structure is the one and only thing keeping the whole shebang unified.
And that brings us to the ultimate, non-negotiable goal of all this engineering: absolute safety during the mission. So how do engineers actually achieve that? Well, it comes down to the incredibly careful selection of construction materials and exact dimensions for every single part of the vehicle. Ultimately, it's just about keeping that skeleton from falling apart under the immense, crushing pressures of spaceflight.
To get there, we've got a 5-part mission blueprint for today. We'll cover 1. Designing for the cosmos. 2. Reality versus rigid bodies. 3. Under pressure, structural loads. 4. Distributing the weight. And finally, number 5, the equations of equilibrium.
All right, kicking things off with part 1, designing for the cosmos. Now we are stepping into a highly advanced world of aerospace structural analysis here. The concepts we're about to decode literally form the foundation of modern space exploration. To give you a quick idea of the depth, this source material is actually targeted at 4th-level engineering students for the 2024 to 2025 academic year. It's rigorous, heavy-duty stuff, but hey, don't panic. There's no pop quiz at the end of this, and we're going to make the whole thing completely accessible and, frankly, fascinating.
Our core objectives, drawn straight from the course, are to understand the basic principles of structural mechanics and to analyze the stresses and strains on these structures under various loading conditions. Basically, we're figuring out the mechanics so we can anticipate exactly how brutal forces will impact our delicate spacecraft.
Moving right along to part 2, reality versus rigid bodies. You know, in engineering theory, there is this ongoing battle between perfect math and, well, harsh reality. The math loves to rely on a concept called a rigid body. By definition, this is an ideal body with zero deformation. That means it remains completely undeformed under any amount of force whatsoever, and all of its parts maintain the exact same relative positions. It's this mathematically perfect, totally impossible ideal where a spacecraft perfectly resists everything thrown at it without so much as a microscopic flinch. But reality check time. A real structure, like an actual working aircraft or spacecraft, is a physical body that deforms under load. Real structures are absolutely not rigid bodies. They bend, they warp, and they shift. This deformation is the actual highly unpredictable environment that aerospace engineers have to conquer if they want to ensure anyone's safety. Which brings us to part 3, under pressure, structural loads.
It's time to introduce the invisible antagonists of our story here. Structural loads, or actions, are essentially any forces pushing, pulling, bending, or twisting the structure. And these aren't just abstract ideas. These specific actions cause dangerous stresses, severe deformations, and displacements across the entire framework of the vehicle. Let's break down how they strike.
First up, axial loads. These are forces applied parallel to the longitudinal or long axis of the structure. Think of aerodynamic drag, for example. Imagine a massive, invisible hand actively trying to stretch or compress our spacecraft end to end as it violently punches through the atmosphere.
Then we've got lateral or transverse loads. These forces apply parallel to the lateral or short axis of the structure. The classic example here is lift. These forces are basically trying to push hard against the side of the vehicle, constantly threatening to snap the whole spacecraft sideways if the structural dimensions aren't calculated perfectly.
Next are twisting loads. These happen when force is applied as a torque to a structure. Just picture taking a wet towel and twisting the ends in opposite directions to wring the water out. That is exactly what twisting loads are trying to do to the metal, the composites, and the crucial joints of a spacecraft.
All right, part 4, distributing the weight.
Because it's not just about the type of force, but exactly how that force makes contact. Engineers have to evaluate 2 very different types of external load distributions: concentrated loads and distributed loads. A concentrated load is a massive force hitting a single localized pinpoint spot on the structure. A distributed load, on the other hand, is a force that's spread out heavily across the spacecraft's surface. Both of them cause deformation for sure, but they require entirely different structural supports and beam designs to safely manage all that stress.
And finally, we arrive at part 5, the equations of equilibrium. This is the ultimate mathematical defense mechanism. I mean, we know the forces are brutal, right? And we know the spacecraft will deform because, as we established, it is definitely not a rigid body. So how do we actually know if it's safe? How do engineers prove the design will survive the mission before it ever even leaves the launch pad? Well, the answer lies in the equations of equilibrium. Engineers use these mathematical models to calculate unknown forces. They look at variables like the number of structural members, which we represent with N, and reaction forces, represented by R. For a structure to be statically determined and mathematically stable, the reaction forces need to equal 3 times the members, or R equals 3n. So if n is 2 and R is 6, we check if R is less than or equal to 3n. It is. So yes, that structure is perfectly stable. It's honestly not just math on a chalkboard. It is literally the difference between a highly successful mission and a catastrophic failure.
So we've seen the blueprint. We know that real structures deform, and that axial, lateral, and twisting loads are constantly attacking the framework. So I'll leave you with this thought to ponder. With all of these brutal forces pushing, pulling, and twisting at every single second, exactly how much deformation is too much before that critical skeleton simply shatters? Thanks so much for joining me on this explainer, and keep questioning the cosmos.